Hello everybody, this is Danny from the University of Campinas. Today I am going to present our paper entitled Towards Deep Network and Application Integration, Possibilities, Challenges and Research Directions. This is a joint work with people at Yale University, Nokia, Telefonica and Ericsson. The collaboration between networks and applications increases the quality and hence the business offering of the former and the performance of the latter. For example, data-intensive science applications, such as the Large Hadron Collider, telescopes, online sources, rely on the networks as one of the key components of their infrastructure for local or global interconnection of laboratories, sites, and data centers. In case of adaptive applications, such as adaptive video streaming over HTTP or Dash application, the streaming video clients execute bitrate adaptation algorithms to select the best possible encoding. Those client-side algorithms may only achieve flow rate equality when the network view is absent. However, if we want to achieve quality of service or quality of experience level equality, applications and networks need to collaborate. Applications, for instance, can provide additional information such as screen size, spectrum, and so on. And the network, having a global view, is in the best position to achieve allocation of resources with a goal beyond flow-based fairness. Also, getting a feedback from the network could allow application to improve the network utilization. So, clearly, the collaboration between networks and applications provides opportunities to both applications to improve their performance and the network service providers to increase the business offering. Because of that, different systems and mechanisms can be proposed to support such collaboration. For example, network providers and applications have considered different Nash equilibrium solutions. ISPs, for instance, attempt to improve the application issues through an infrastructure upgrade, usage-based charging models, rate limiting, and termination of services. On the other hand, applications attempt to improve the network efficiency, having flexibility in shaping communication patterns, and having flexibility to adapt to network topologies and conditions. However, such solutions are largely application network oblivious, making the interaction between networks and applications inefficient. Other existing solutions adopt a best effort or black box request approach. In the first one, applications submit the complete requirements and the network computes and enforces the optimal resource allocation for applications. In the second one, applications submit the amount of network resource needed and the network returns success or failure based on the resource availability. Those solutions have limitations on the privacy of application and scalability or have inefficiency in finding the optimal resource allocation for applications. In this paper, we propose to explore a more integrated architecture that takes a deep network and application integration approach, NI approach. The NI approach seeks to enable a tighter integration amongst applications and networks, so that the application can be adapted to a particular state and context, and the network can be adapted to a particular requirements. Specifically, we explore the possibilities of NI in two aspects: application-aware networking and network-aware applications. Application-aware networking in the top-down direction is related with the expression by the application of the required properties and characteristics needed to be supported by the network. And network-aware applications in the bottom-up direction is related to the exposure by the network of information that can be processed and consumed by the applications. Now, let's give a little more detail in each aspect. So, applications have varying needs for network latency, bandwidth, packet loss, etc. However, such applications requirements are often unknown to the network because applications and networks are decoupled. Therefore, one concrete aspect of NI is adding application knowledge to the network so that applications can express finer granularity requirements. There are different possibilities in implementing NI by application-aware networking. For example, the network infrastructure can provide better support for applications, introducing different capabilities to create different networks, slices, or quality of services, and also scheduling each packet according to the application level deadline, or the newer thread where the application can also provide in-network computation or in-network storage. Several research activities can be proposed exploring the possibilities of adding application knowledge to the network. Magellan, for instance, is a programming environment for users to specify a global packet or in-network processing logic, which is expressed in a general-purpose language. Then, Magellan automatically generates both data paths in every single network device, and runtime for control plane. Socket intent is a proactive application-expressed approach for multi-access networks connectivity. Socket intents allow the application to share information about their communication patterns, such as preference, characteristics, expectations, and so on. Application-aware IPv6 networking proposes a framework for using IPv6 extension header to convey the application requirements along with the packet to the network. Application awareness introduced by APN6 can benefit different use cases, such as SLA warranty, network slicing, and network measurement. PANE introduces the concept of participation networks, in which the networks provide a configuration API for applications to control a software-defined network. The proposed PANE API is used in different use case applications in which information from applications benefits network flexibility, configuration, and performance. Regarding real deployments, here we have a couple of examples. Big Data Express is a data transfer service for big data science. It provides an application-aware SDN-enabled network service to program networks with provisioning of multi-domain end-to-end network paths. Big Data Express is deployed in several research institutions, such as Starline, Siena, etc. The same systems provide an intent-based interface to allow the application to express high-level service requirements. A multi-institution testbed had been deployed at TOE laboratories and different university facilities. On the other hand, applications running over networks face challenges due to the lack of network information. Applications can benefit from network information exposure to make them more flexible in terms of rate adaptation, transmission time, served path selections, among others. Therefore, the other side of collaboration is network-aware applications, and there are many possibilities as well. For example, many applications can be somehow flexible. They have possibility to conduct transport selection capabilities based on the network state, for example, packet loss. Application can be adapted in terms of transmission time, system time, locality, for example, which servers to use in multiple replics, which path to use, and so on, and rate adaptation as well. Besides, if network can provide programmability support, then applications can also use that support to conduct network compute selection. There are different proposals introducing the benefits of network awareness for applications. For example, Peer-for-Peer, provider portal for applications, is a framework to enable a better cooperation between network providers and network applications. Peer-for-Peer eye trackers accelerate the content distribution and optimize the utilization of ISP network resources. This figure shows a peer-to-peer application example with app trackers using peer-for-peer interfaces in the eye tracker to request network policies and costs. Another maturing example of NIE protocols is ALTO, Application Layer Traffic Optimization. The IETF ALTO protocols provide network information with the goal of modifying network resource consumption patterns while maintaining or improving the application performance. The information is exposed as abstract maps, network maps, cost maps, unified property maps, etc., in order to protect the information privacy and improve the scalability. Comcast, a large broadband internet service provider in the United States, deployed a peer-for-peer based open framework. Specifically, peer-for-peer eye trackers were used to allow peer-to-peer network to optimize traffic between each ISP while improving the download performance for peer-to-peer clients. Another much larger deployment is Flow Director from Venus, an ISP hypergiant collaboration system. Basically, Flow Director has three main functions. It collects data to determine the state of the IXP network, then it computes the bits mapping, and finally Flow Director communicates this information with the cooperating hypergiant in near real time via multiple protocols, including ALTO, BGP, and so on. So, previous slides exposed huge possibilities of NIE. However, releasing it is not trivial. In this slide, we review the key challenges for systematically releasing NIE. One challenge is that applications are lacking of visibility of available and sharing network resources, resulting in poor performance. Existing network resource exposure mechanisms, such as graph-based abstraction or one-big switch abstractions, expose all sensitive information or fail to capture the resource sharing between virtual flows requests. The second challenge is the lacking of a generic and flexible mechanisms for application to specify and discover the network information. Existing solutions provide application interfaces to discover an end-to-end cost of different packet spaces, However, this information is derived from a fixed resource allocation of the network. An application don't have the flexibility to discover additional network resources that can satisfy their needs, for example, on-demand routing or waypoint routing. Network information exposure and discovery play an important role in releasing NI, but can also raise security and privacy concerns. For example, applications queries may expose proprietary information, such as internal data flow policies, or may reveal too much information about the individual clients. For the network side, too much information may be exposed if aggregation or transformation mechanisms are not considered. To address the previous challenges, we propose the initial design of a generic PED framework, Possibilities, Exposure, and Discovery Framework. The PED framework consists in three novel design points. Number 1, mathematical programming constraints as a unified and compact resource representation. Number 2, a declarative language for application to express their intents on discovery network information. And number 3, an efficient compiler to translate a resource discovery query to constraint programming problems and discover corresponding network information. Regarding the design point number 1, in PED, when the network needs to spread the information for a set of flows to applications, it uses mathematical programming constraints to capture the resource availability and sharing information of those flows, providing a unified resource representation. To give an illustrative example, consider the network topology in this figure. In this case, the application wants to reserve bandwidth for two flows, F1 and F2. The routes for the two flows share common links, L3 and L4. Therefore, it's not possible for both circuits to reserve 100 megabits bandwidth. Then, using mathematical programming constraints, the PED framework will generate a set of linear inequalities to provide a compact representation of the available bandwidth of flow through the network. In this case, X1 and X2 represent the available bandwidth that can be reserved for S1 to D1 for flow 1 and S2 to D2 for flow 2 respectively. Each linear inequality represents a constraint on the reservable bandwidths over different shared resources by the two flows. For example, this linear inequality indicates that both flows share a common resource and the sum of their bandwidths cannot exceed 100 megabits per second. Regarding the design point number 2, resource discovery language, PED introduces a declarative language that allows applications to express flexible resource discovery intents. Specifically, the language uses a resource filtering design which allows applications to define predicates on packet space. This means different sets of flows, and predicates on resources. This means particular resource attributes that applications are interested in discovering. And the language uses an SQL-style semantic which is familiar to both application and network engineers. To give another illustrative example, consider a case where the application has two flows to transmit and wants to find the bandwidth and delay the network can provide for those two flows. The first flow is a HTTP flow from source IP 10.0.0.1 to destination IP 10.0.0.2, and the other one is an FTP flow from source IP 10.0.0.3 to destination IP 10.0.0.4. In addition to the basic reachability, the application wants the HTTP flow to pass a firewall middlebox and then a DPI middlebox before reaching the destination, and the bandwidth of the FTP flow to be at least 100 megabits per second. Finally, the application specifies its resource discovery intent for those two flows. So, a resource discovery intent is expressed as a sequence of flow specification statements, a sequence of resource requirement statements, and a query statement. In the flow specification statement, it defines a flow or a set of flows about which the application wants to get the resource information. In this case, the application first expresses the specifications of two flows, F1 and F2, and then defines a flow set containing those two flows. With the resource requirement statement, applications express the basic requirements or resources provided by the network for a set of flows. In this example, the application specifies its basic requirement for those two flows, such as the firewall and DPI waypoint requirement for flow 1 and the minimal bandwidth requirement for flow 2. We can also use the resource discovery language to express other common resource requirements of applications, such as bidirection symmetry, node and linked joinedness, blacklists of devices, and so on. Finally, the application uses an SQL-style query to assemble the previous flow specification and resource requirement and express the resource discovery intent. In the example is to find the bandwidth and delay the network can provide for flow 1 and flow 2 subject to the application's requirements. Once a resource discovery query is received, PED first compiles the requirement filter predicates into a set of logical constraints, and then leverages state-of-the-art solvers to search for qualified configuration that satisfy the application's requirement. So, PED uses different logical constraints to compile the application's requirements. For example, given any flow Fi in the query statement, the application requires the network to ensure reachability of this flow. This means there exists at least one path from source node Si to destination node Di. Internally, PED compiles this requirement using a set of binary variables, B sub UV for flow Fi, whose value is 1 when link UV is used to forward traffic of Fi in the network. In case of bidirection symmetry, given a flow Fi, the application may want to force the traffic in both directions to use the same single path. To do this, PED decomposes Fi into two flows, Fi in and Fi out. For blacklist of devices, given a flow Fi, if the application wants that Fi should not pass a device, for example a middle box B sub M, using this logic constraint, PED can compile such requirement. In addition, given two flows, Fi and Fj, if the application wants those two flows being transmitted along two link disjoint paths, PED uses these logical constraints. Or similarly, if the application wants those two flows being transmitted along two node disjoint paths, PED compiles this requirement using this logical constraint. PED is also able to compile other requirements related to waypoint traversal, quality of service metrics, and limited sharing risks. Having compiled a PED requirement into a set of logical constraints, we can leverage state-of-the-art solvers to search for a feasible configuration that satisfies the requirements of the application. However, topologies of data center networks, for example FAT3, are designed to have a large number of paths for a pair of edge hosts to achieve the full bisection bandwidth. For example, in this FAT3 topology with only 4 pods, the number of paths between two edge switches in different pods is 272. Therefore, for a set of flows, the number of all the combination paths would grow exponentially, as the number of flows does. As such, given a resource discovery intent for a set of flows, the feasible resource search space is so large that directly sending all the logical constraints to a solver is impractical. To address this issue and find the feasible resource that satisfies the requirements, the search space decomposition algorithm, SSD algorithm, decomposes a large set of logical constraints into multiple disjoint subsets to improve the efficiency of resource searching. The SSD algorithm is built in two key insights. Number one, given two sets of flow F1 and F2, if the application doesn't have any resource sharing requirements, for example, quality of service metrics on those two flow sets, the feasible resource for both sets can be searched in parallel, and each of them has a smaller search space. For example, consider two flows, F1 and F2, where the requirement only specifies that F1 must pass through a firewall middle box. In this case, PED can search for a path and the corresponding resources that satisfy the reachability and waypoint traversal constraint of F1, and for path and corresponding resources that satisfy the reachability constraint for F2. For the second insight, if the application has resource sharing requirements on two sets of flows, F1 and F2, but the data center network can provide the joint feasible resource search space for each set, the feasible resource for two flow sets can also be searched independently. In this example, application specifies that the path F1 and F2 must be node disjointed. However, the end hosts of F1 and F2 are in two separated pods. Therefore, even if F1 and F2 has a resource sharing requirement, PED can perform searches in two spaces in parallel and still get the feasible resources, satisfying such a resource sharing requirement. Finally, after qualified configurations are found, PED encodes the resource information of the configurations, for example bandwidth sharing, in a set of mathematical programming constraints and sent to the application. We preliminarily evaluate PED in different scales of FAT3 topology using different workloads. Specifically, we evaluate the performance of two versions of our design. SSD, that is the full version of PED, where the SSD algorithm is enabled, and baseline, that is a simplified version of PED, where the SSD algorithm is disabled. We generate different application workloads by randomly selected different amounts of end hot pairs to compose different float sets. We also generate 3 different ratios of resource sharing requirements in the original logical constraints. For example, baseline 100% indicates that all the original logical constraints are quality of service metrics requirements for all flows. Then we measure the resource discovery latency of both versions as the elapsed time from the time when the compiler finishes the compilation to the time when the feasible configuration of the original search problem is found. In both figures, we can see similar results either with a fixed factory site with varying numbers of flows and with varied factory sites with 40 flows. For example, results show that the PED with SSD enabled always has a lower discovery latency than the one with SSD disabled, regardless of the ratio of resource sharing requirements, demonstrating that efficiency of the first and the second phases of the search space decomposition. Finally, regarding key future research direction towards deep network and application integration, we have, for example, that a common setting for many novel applications is that the traffic from a source to a destination traverses multiple technological or administrative domains. Therefore, it's necessary to design multi-domain composition mechanisms so that network information in multiple domains are adapted together to a single and consistent virtual abstraction. In addition, traditional interdomain routing protocols, using for example the BGP model, provide very limited mechanisms for network operators and applications to achieve flexible end-to-end routing control. Therefore, more research efforts in this direction are required to expose more control and programmability beyond just information. As we mentioned, resource discovery techniques increase the optimal resource allocation, but at the cost of communication and computation overhead. A possible optimization is to proactively discover the resource information. Another alternative is to explore to use those pre-computed abstraction to quickly project the resource abstraction for the applications. To deal with network information exposure issues, mechanisms to ensure that information is transformed or aggregated need to be also developed. As next steps, the idea is to extend the PED architecture to include different southbound interfaces such as OSPF, BGP, and flow-based protocols such as NetFlow or SFlows. And regarding the experimental evaluation, we will consider more complex and real environments under different network dynamics and network sites. Okay, I would like to thank you for your attention and feel free to ask any questions.